Hello students, so continuing our lectures on nanoelectronics and especially the quantum dot between two electrical leads. Now this is the circuit that we have discussed in our previous lectures, how a voltage source is connecting the two leads with an insulating with a metallic quantum dot in between. And there are two tunnel junctions formed, one here and one here, and let's name it as A and B positions. And these tunnel junctions are basically insulating regions which are separating this quantum dot from the external source, from the external power source. So, although it is a complete circuit, we are calling it a complete circuit. There are capacitance developed at these 2 points, and these capacitance are also called the leaky capacitance. That means there is a travel, electrons can pass through the insulating region between these capacitance. So the sleepy capacitors are also represented by a capacitance with a resistance in that. So there are two capacitance formed, C and CB, and the total capacitance since they are in series is CS. Now also, since these are the tunnel junctions, so you will have the tunnel resistance associated with each of these junctions. So the tunnel resistance for the junction A is RTA dash, and for the junction B is RTB dash. The total charge that is existing at the point A is the capacitance into the voltage at this point, that is CVA dash, is corresponding to the B point. Now, when a charge transfer has taken place, so similarly, there will be a change in the charge transfer, in the change transfer present. So, this is the difference between the two charges at points A and B. Now, the energy stored in the capacitors can be measured by this usual, this very known equation, that's Q square by 2A, and the total voltage is, according to Kirchhoff's law, will be the sum of voltage drop in positions A and B. So Vs is equal to Va plus Vb, and now Vb can be written in terms of this relation as Vq by Cb, and after electron has traveled through, so we can add an extra electron to it. So that makes it not one, more than one, that's any, we can add this one to here. So this becomes QE plus Na. So we can put this equation, and ultimately this is the value of VA that we obtained, voltage drop at point A, that means in this junction, this one. Similarly, there will be a voltage drop in point B, which will be this, and the total stored energy in the capacitance will be like this. Now since there is a tunneling, so there must be a work done. So that work done is by means of a power through which the transfer of charge is taking place. So if we integrate the power with respect to time, we get the value of change in charge into the voltage supply. So this is the total net charge this is the total net charge transferred by the power in time.